Hi, this is George Woodbury from College of the Sequoias in Visalia, California, and this is a review for my intermediate algebra class for their Chapter 8 exam. The topics we'll be going over: solving linear equations and absolute value equations, solving linear inequalities and absolute value inequalities, graphing linear functions and absolute value functions, and finally a review of factoring polynomials and solving quadratic equations by factoring. It's a series of 23 problems. If you'd like a copy of the problems, you can reach me at the contact information at the end of this video, and I can send you a PDF of the problems. First problem, a linear equation. We want to begin by simplifying both sides. So here that's going to include distributing and maybe combining like terms. Distribute the 3. Then combine the like terms on the left, 6x and negative x. 6x minus x is 5x minus 15 equals 2x minus 48. We need to collect all the variable terms on one side. I can do that by subtracting 2x from both sides. Next, I want to collect all the constant terms on the other side, so I'll add 15 to both sides. And I get 3x equals negative 33. Divide both sides by 3. And I have x equals negative 11. So my solution set is negative 11. Problem 2. Absolute value equation. Remember, the first step for solving these is to isolate the absolute value. So if I subtract 6 from both sides, I have the absolute value of x minus 9 equals 7. And recall that an absolute value isolated compared to a positive number, we split this into two equations. X minus 9 equals 7. X minus 9 equals negative 7. And I can solve these by adding 9 to both sides of both equations. And I'm left with x equals 16, or x equals positive 2. Solution set 2, 16. So that was isolate first and then split. Same idea here. You want to be careful. Sometimes when we see a negative number on the right side, we stop and think there's no solution. But you can't tell until the absolute value is isolated. Adding 9, we find that we're comparing absolute value of 2x plus 1 to positive 5, which we can solve. Splitting that in half. 2x plus 1 equals 5, or 2x plus 1 equals negative 5. We solve both of these by subtracting 1 and dividing by 2. 5 minus 1 is 4, divided by 2 is 2. On this side, negative 5 minus 1 is negative 6, divided by 2 is negative 3. And so our solution set is negative 3 and positive 2. Here I have just a basic linear inequality, no absolute value, so I don't have to worry about trapping or splitting. I just want to isolate the variables, so I'll add 7 to both sides. 3x less than or equal to 24, and I'll divide both sides by 3. Since I divided by a positive number, I don't have to worry about changing the direction of the sign. On the number line, less than or equal to, we start with a solid point, and then we shade to the left. In interval notation, that's going to be negative infinity, comma 8, and the 8 will get a bracket because of the solid line and the solid circle, the equal sign in the solid circle. One to be careful with here, another linear inequality, is that when we isolate the variable term, it has a negative coefficient. So when I divide through by negative 2 on both sides, I have to change the direction of this inequality sign to become greater than. So the solution, x is greater than 6. On the number line, that's going to be an open circle at 6, no equal sign, and we're going to shade to the right. In interval notation, it starts at 6, which gets a parentheses because of the open circle, and it goes to infinity. Here's a compound inequality where we're trying to isolate the variable inside the middle piece. Subtract 1 first. Negative 6, less than 3x, less than 27. Divide through by 3, positive 3, so we don't have to worry about changing signs. Negative 2 is less than x is less than or equal to, sorry about that, 9. On the number line, open circle at negative 2, close circle at positive 9, and we shade between those. Negative 2 comma 9 for the interval notation, parentheses, open circle, brackets because of the closed circle. Here we have an absolute value less than a positive number. To solve this, we're going to trap x minus 6 between negative 4 and 4. We want to isolate x on the middle branch, so we'll add 6 to all 3 branches. And we're left with 2 less than or equal to x, less than or equal to 10. On the number line, it's going to be closed circle at 2, another closed circle at 10, and we shade between those. Interval notation 2 comma 10 in brackets. Now again, absolute value less than a positive number is the situation where we trap the absolute value. In this case, we're going to be ending up with an absolute value being greater than a positive number. After we subtract the 3, we get 13. That's a case where we split this into 2 inequalities, 2x plus 3 greater than 13, or 2x plus 3, change the greater than to a less than, and the 13 to a negative 13. Then we solve both of these by subtracting 3. And dividing by 2. On the number line, that means an open circle at 5, shade to the right, x less than negative 8, open circle at negative 8, and shade to the left. Interval notation, the first interval is negative infinity, comma negative 8. Union, the second one is 5, comma infinity. Recall that we have to isolate the absolute value before we can do anything. And here I have the absolute value of 3x minus 1 greater than negative 3. Absolute value is going to be non-negative. Think of your favorite positive number. Will a positive number be greater than a negative number? Sure. This one is true all the time, so our solution set is the set of all real numbers. Recall that when you compare an absolute value to a negative number, you're either going to have no solution or the set of all real numbers will be your solution set, and you've got to figure out which is which. Okay, again, we begin by isolating the absolute value here. Add 15 to both sides, and we're left with the inequality x plus 9, absolute value of that, is less than negative 7. Okay, again, comparing an absolute value to a negative number is an exception case, and can a positive number or a 0 be less than a negative number? That's impossible. This is always going to be a false statement, so we say this inequality has no solution. Right, one last one, we have an equation where the absolute value is already isolated compared to a negative number. Again, this expression, absolute value will always be non-negative. Can a non-negative number ever be the same as negative 9? No. This is a false equation and has no solution. Graphing linear functions, remember that a linear function, f of x, is of the form mx plus b, so we know that the slope of this line is negative 2/3, and we know that the y-intercept will be at 0, 8. So a real quick sketch of the graph. 1, 2, 3, 4, 5, 6, 7, 8. Let me just move over 3 for now. We're going to have a point at 0, 8, and then because our slope is negative 2/3, we go down 2 and 3 to the right. Sorry about that. And then we just draw the straight line that goes through those 2 points. Another one, same idea. Start at 1 on the y-axis, and the slope here is 5, so that means up 5, 1 to the right. Start at 1, up 5, 1 to the right, and see if I can do this without a ruler. Wow, almost straight. There's the line. To graph absolute value function, we want to find the point of the v where the graph turns around. Remember, absolute value, v for value. The v point is going to be at 5, -4. Recall x minus h plus k. X minus 5, x minus h is 5. This is the same as plus -4, so -4 will be the value of k. A lot of students think of this as the opposite of the value inside, but the same as the value outside. Really, you want to think about trying to get into this x minus h plus k form. Either way, our absolute value, 1, 2, 3, 4, 5, 1, 2, 3, 4, has a v point here at 5, -4. Now, because it's a plain x, not a 2x or a 3x, that means its slope is 1 on the linear portions, or -1, depending on which direction you go. There's no negative sign in front, so we know it opens up. So I'll go up 1 and out 1 a couple of times, and then I just draw the v that passes through. Remember that the domain for any absolute value function is from -infinity to infinity. An arrow on the left indicates -infinity is the beginning of the domain. An arrow to the right means that infinity is the end of the domain. Now for the range, we're thinking bottom to top. How low does this graph go? Well, it goes down to a height of -4, so that's where the range begins. How high does it go? Since it has an arrow pointing upward, we know it goes to infinity, and we put a bracket with the -4 because it is included in the range. Similar problem, a couple things that are different here. First, this minus sign means that it will open downward rather than upward. We can think of this as x minus -3 in the parentheses. So our v point will be at -3, 1. -3, 1. This opens down, so down 1 and out 1 a couple of times. And there's a quick sketch of our graph. The domain, again, all real numbers. For the range, because it has an arrow pointing downward, we know it goes down to -infinity. The maximum value here is +1, bottom to top. So -infinity, 1 is the range. I'm going to finish off with a few factoring problems and then one equation that we'll solve. Basic trinomial, leading coefficient of 1. We'll factor to be of this form with two binomials. I want two numbers that multiply to 20 but subtract to be 8. I'll worry about the signs in a minute. Those two numbers are 10 and 2. I want to think about how do I combine a 10 and a 2 to make a -8. I can do that if it's a -10 and a +2. And my last check, I multiply the last two numbers to make sure I get the last coefficient. -10 times +2 is -20. Same idea, two numbers that multiply to 24 but add to 10 are 4 and 6. And they're both going to be positive. Here we have a leading coefficient that's not 1, but it is a common factor to all the terms. So I can factor that out first. That will stay in front for the remainder of the problem. Inside the parentheses, I have a regular trinomial leading coefficients 1. So I want two numbers that multiply to 22 but subtract to be 9. And those are 11 and 2. plus 11 minus 2 will get me a positive 9. Positive 11 times negative 2 is negative 22. So this is correct. Okay, here's the trouble. Leading coefficient's not a 1, but the 2 is not a common factor to all the terms. So we have to go by trial and error here. X times 2x is the only way to make 2x squared. 24 could be 1 and 24. It could be 2 and 12. It could be 3 and 8. And it could be 4 times 6. And we've got to mix and match until we find the right pairing. We do have some things in our favor here. Namely that the factor with 2x can have a common factor. So the 24 can't sit with the 2x because 2 and 24 share a factor of 2. The 2 is out, the 12 is out, and really the only other number that could be with 2x is the 3. So I'm going to try it with the 1 and the 24, and then I'm going to try it again with 8 and 3 with the 2x. If I look at the inner and outer products of the first one, I have 1x and 48x. That will not give me negative 13x. But if I look at this one, here's 16x in the middle and 3x on the outside. To make negative 13x, I can do it if the 16 is negative, which will mean the 8 is negative and the 3 is positive. X minus 8 times 2x plus 3. There is another method you could use here, by the way. It's called the AC method. If you multiply 2 times 24, that's 48. Think of two numbers that multiply to 48 but subtract to be 13. 3 and 16 are the right pair, so I could break the negative 13x up to be plus 3x minus 16x, and then I can factor by grouping. First pair has a common factor of x. Second group has a common factor of negative 8. And I can pull out the common 2x plus 3 times x minus 8. Same result, different direction. What we have here is a difference of squares. Two terms. All the exponents are even. All the coefficients are perfect squares, so I can rewrite it as a difference of squares. And remember that for factoring, that's going to be the first one plus the second times the first one minus the second. Difference of cubes. This is the same as x cubed minus 6 cubed. You should memorize or be familiar with the different cubes. This factors to be a binomial times a trinomial. For the first one, just drop the cubes, x minus 6. For the second one, I like to have my students write out the first factor 3 times, the second 3 times, group them in pairs to figure out the 3 terms in the trinomial. X times x is x squared, x times 6 is 6x, 6 times 6 is 36. And then to remember the signs, a friend of mine gave me this SOAP. The first sign is the same, S for same. The second sign is the opposite, O for opposite. And the last sign is AP, always positive. Then he says something like, factoring difference of cubes is dirty business, always use SOAP. Here's another, this time we have a sum of cubes. This is going to be x cubed plus 9 cubed. Start by dropping the cubes. Again, write each of the terms 3 times, group them up in pairs. X times x is x squared, x times 9 is 9x, 9 times 9 is 81. Same, opposite, always positive. One problem to go, and that's solving a quadratic equation by factoring. Whenever you have x squared in the mix, you want to get everything on one side equal to 0. So I'm going to subtract 2x and 25 on both sides. That's going to give me x squared minus 5x minus 36 equals 0. Once you have everything equal to 0, you can factor the quadratic expression. Set each factor equal to 0, because if two numbers multiply to be 0, then we know that one of them must be 0. Solve the first equation, x equals 9, and the second equation, x equals -4. So our solution set is -4, 9. And you can put those in whichever order. I always put the lower one first. Okay, if you have any questions or comments on these problems or any other problems, or if you've got a request for a video that I can put together for you on YouTube, you can reach me through the contact page on my website, and the address for that is georgewoodbury.com. Thanks for watching, and good luck, especially to my students, and I'll be seeing you.